I think I start with a couple of organizational points. I'm not going to share it, but you can see it in the agenda. In September there will be no working group meeting because I think at least I will be on holiday and most other people as well. Or maybe I can ask Ralph if he's available and if he has something. But like then maybe you will make a meeting, but I assume not. From my side, there will be no meeting in September, and the next meeting will then therefore be on the 2nd of October. Just to let you know. Yeah, I think I wrote you also this email about a bit of a reminder. So the last meeting was recorded in audio, but I had a listen through it. And I would like to later also continue this discussion that after Enrico's presentation, of course, no one of the people that discussed then are here now. So therefore it's going to be fun. But someone that is here is Jannik. We used to be colleagues at Fraunhofer, and we met again at this ROS meetup that happened in Renningen. So if you haven't been there, I'm sorry, but we had a really nice meetup in Renningen. And there Jannik mentioned that they are also using behavior trees and working in the field of deliberation, deliberately deliberating robots. And Jannik has agreed to give us a short presentation of their experiences, and I would be happy to learn what your take is on the topic.
Yeah, so thanks for the introduction. I mean, it's the first time anybody of NODE Robotics joins, so I hope the presentation fits what you're expecting, or at least fits the scope of the working group. So let me start presenting, and then let's see. I mean, we can join.
There are no fixed rules usually. All presentations are welcome.
Okay. Yeah, I mean, we started with we are interested in joining, and then okay, please make a presentation, and there I am. So 10-15 minutes deliberation at Node, quirks and features of behavior trees, state machines, whatever we use to make robots behave. So first of all, since we're new in the working group, who we are a spin-off of Fraunhofer IPA. We were founded in 2020, based in Stuttgart. Like Christian already said, former IPA colleagues. Now we are 30 employees and we have already over 500 AMRs with our software in productive use. One thing that isn't on this slide, we are a software company and we provide navigation software, and our mission is to make mobile robots easy to use. So where do we start? I mean, we are all ROS users, so the situation, if you start with a mobile robot, you can get to the situation where localization is solved quite quickly. There are great open source packages. For later use, you might need a bit of adaptation or a new package, new technology. That's there. Global planning, same. I think Navigation 2 provides a great way and great tooling for global planning, for example. Local planning as well. And then you're here running RViz. That's not really a productive use case because you can't run RViz in production. There's just a lot of the stuff lacking, and that's where we started looking into the topic of deliberation. So what's the first challenge we faced and how did we solve it? We have a module that's called MBF State Machine. it implies move-based flex for us, because at the time there was no navigation tool. There was move-based with its limitations, which have been lifted now, and there was move-based flex, an open source package by Magazzino. The main difference and the great difference there was that it allows fine-grained control. So not only an action, that's the goal, go there, but also get path for planning, execute path, and all the recovery actions. At the time, I think most of us in this field were using Smash, SMACH, or FlexP, or one of the state machine implementations. I think it was even before the first announcement of behavior trees. So we went there. We had a few bugs. We had a few new states. So things that took quite a while, parallelism, getting action states race-free. We created a few submachines, factories that produce submachines, different controllers. So we ended up with, really a state machine that could do quite a lot of things. So you could select which controller should run at which situation of the navigation task. You could implement waypoints for navigation, which isn't just out of the box. Also resuming, there were interaction zones, so the robot could ask for leases to enter and how to react if the lease is granted, revoked, and returned, and also triggering recoveries. Triggering recoveries brings us to the next task of deliberation, and I added a super short excursion here. Navigation recoveries. What was the problem? Not all recoveries that a robot might offer make sense in every situation. So there we started again with kind of a state machine that just selects appropriate recovery behaviors for a given situation, and also takes care of how many retries. So super tiny YAML representation of a state machine. The implementation, of course, is a bit more complex, but we got used to writing state machines in YAML back then. Maybe an interesting design choice that will come in later. So, like I said, our large state machine triggered a smaller state machine, which supported a few features. I mean, downsides of the state machines in general, parallel execution is hard, led to races. Documentation wasn't as easy with the tools we had back then. Quite a manual process. I mean, you see the UML is drawn by hand. Introspection, especially runtime. We covered, or we tackled a few issues where we had runtime issues, but only when introspection was enabled. And that's super hard to fix a system that really breaks down if you want to look at it. And extendability just reached a point where it wasn't extendable anymore with the different factories producing sub-state machines we had in place then. So today, that's the past. Now we switched to behavior tree. We were obviously inspired by what Navigation 2 provided at the time we were switching. Basically the same tools, or basically the same features. We wanted to select controllers at runtime. We wanted waypoints. We wanted interaction zones. We wanted recoveries. Now we already also select them in there, so that's quite nice, a bit of unification. And the behavior tree CPP tooling helped us here. So introspection got easier, designing the tree got easier. There were a few things we had. Mostly we needed a lot of backporting from navigation 2 for the ROS1 stack there. I mean, that's one of the costs that come with maintaining a ROS1 stack and not switching to, or not early adopting ROS2. So that's fine. So it's something. What is it? The robot can now drive, and it can drive in production environments. So great first task for behavior of a robot. But of course, driving isn't enough. So we started missions. Short background for everybody who's not in navigation or based in Germany. There is a standardization effort working on standardizing the interface between mobile robots, AGVs, and master control systems, so fleet management system. In super short, missions are JSON serialized, transmitted over MQTT. So we always have we have quite an open data format, but always the similar objects and some wordings or some vocabulary from VDA 5050. We have nodes which correspond to one point on the map. We have edges connecting those nodes. Actions can be associated to nodes or can be associated to edges, and instant actions that aren't associated to anything but should run instantaneously. So there, the most meta feature that we needed to support mission execution. We know from the mission definition where to go and where to do what. So that's already quite valuable. But how to do that? We dynamically build trees. So since with the mission definition, it's possible to send the robot to an intermediate place, tell him, yeah, wait here, and you will receive an update where it then you get more information how to proceed. So that's where this dynamically built and extending tree comes in place. So we parse the JSON, and the structure of the JSON is super close to the structure of the tree that is built, which is quite nice in terms of looking at the tree, and then you can easily see where we are at our mission. And one side note or a few things that came out of this design, we have an extendable sequence now. So a sequence that doesn't finish until it knows that we are at the end of the sequence. So the great thing with our missions, we know how long we expect them to be. And with this expectation, we can, in the sequence, see if we are actually completed or if we are still waiting for an update, for example. The whole life cycle of nodes got changed with this dynamically building trees. So now we have decorators that actually own their children compared to the default or compared to the behavior tree CPP implementation, where one root owns everything. And yeah, just a few control nodes to preempt a preempting parallel node that allows us to do stuff in parallel until one of the children finishes. That's one thing we use, for example, for this. Sorry, I mixed two components. That's also one of the action implementation. So we can finish actions there and continue with everything that ran in parallel that shouldn't run anymore. Unfortunately, by dynamically building and extending the tree, we again lost almost everything from behavior tree CPP. So GROUT doesn't work anymore as the biggest downside. And without GROUT, the loggers, there are some loggers that still work, but they have to manually be instrumented. So it's quite nice. We can use nodes. We can all the nodes, decorators, control nodes, and the leaf nodes. But everything else isn't of too much value there. Another layer of behavior trees there. As I mentioned, so I'm running quickly through all the occurrences of behavior trees, for example, in our stack. As I mentioned, actions. VDA 50/50 actions describe anything a robot can do. So it can be going to a charger, docking to a charger, starting the charge. It can be load handling, which involves multiple steps and fallback behaviors. It has to be different for every robot, maybe even for every application. And because it's such a custom thing, we needed a lightweight configuration. We still, because I mean, the parent of our VDA 50/50 execution relies on behavior tree CPP. We still rely on behavior tree CPP, but we dropped the XML description and instead opted again for YAML. So we have, if I guide here quickly through the code to get an idea, basically we have root nodes or leaf nodes, sorry, that just trigger actions. And then we started with, and then here I think I will go from the root. We have the pick up retry action, which is actually a sequence of the check card action, the line grab sequence, and the blink action. And then we transformed the whole tree or flattened the tree into those basic structures. So you can specify it's a sequence or a fallback, inverter, decorator, and then compile your whole behavior using YAML. It's quite nice for short stuff. So we see here a sequence has not more than 3 sub-trees or sub-behaviors. But if it gets complex, we still support the XML file, so that's nice. Yeah, we're again building dynamic trees. Somehow that's a thing. And YAML for tree definition is quite common, but we don't think it's commonly used for behavior tree CPP. So that's why I wanted to show it here. And yeah, with this YAML tooling, we again lost almost everything. Common topic, losing everything we are offered. Yeah, the robot just got productive nonetheless when it knows what to do. And there, I think, is the final step that's missing. Where does the robot know what to do? General behaviors, other challenges we faced in not necessarily in production, but more in warehousing scenarios. There were customers who don't have warehouse management systems, and they just wanted to automate a human worker walking around the warehouse, looking for jobs, taking on the jobs, and then executing them. And this one posed quite a challenge, especially for multiple robots, and it required to encode the domain knowledge. So the task sounds easy. The robot goes to a pickup location. If the robot finds something, it picks it up, it brings it to the drop-off location, drops it off, and looks for the next job to do. But where to look for, when to look for, that's everything fine. I mean, Quirks, none, maybe networking, because the way it's set up with multiple robots, we faced some issues with ports that were blocked or needed to be rerouted. So That's more a deployment issue. The downside, I explained the task to you, but implementing it was quite complex, and robotics is hard, and all the things you need to consider, all the recoveries, all the fallbacks, everything charging related, quickly started to blow up. And that's already one part of my conclusion. So super nice compared to super nice development, unified use of behavior tree CPP. So our whole software stack, wherever we need something regarding behaviors, we can use behavior tree CPP. We start accumulating a growing collection of nodes and trees. We did a lot of backporting of the stuff that is available open source, but not for the operating system ROS versions we use. There's a varying amount of tooling. For developers, it's quite good. For end users, especially in the last case I presented, it's quite hard to bring an end user to properly encode everything. And implementing state machines and behavior trees work depends on if you really want to implement them as state machine, or as we did it with this dynamic building approach. With that, thanks very much. I hope it was interesting.
Yeah, thank you very much, Jannik. I guess Guillermo has already a question.
Yeah, thank you so much, Jannik, for the presentation. What I wanted to know is, so if I understood correctly, you are basically mapping the actions coming from VDA 5050 to behavior trees, which means that the server is somewhat kind of controlling the robot in detail. My question is, how do you go with I don't know, the decision making when there is a decision that should happen on the robot, like on sensor level? So is this encoded in the behavior tree itself, or are you passing the information up to the server and then you're solving it there and sending back the answer?
Actually, not the easiest question to answer, because it highly depends. So the last case I presented, where the customer just had no warehouse management system, there we let the server do the decision what to do next, just for opportunities of load balancing and evenly spreading out. If it's decidable on the robot, so if it's something where you can pick A or B and it doesn't really matter, then we keep it on the robot. So five different boxes to pick up. There's the same thing in every box. Just pick one, that's fine. That's on the robot. But as soon as we fall back and go into this unexpected fallback behavior, then it's usually escalated.
And the decision in the robot is basically in the behavior tree. So in the behavior tree that you're choosing, the behavior tree is modeled with this choice in mind, that there could be an order where you have to decide, and therefore you can decide. Okay, understood. Thank you.
That's in this YAML file I showed you, there was the selection encoded until it would fail. Yeah. I mean, it's hard to read and to present in a short time.
Thank you so much.
Yes, Calvin.
Hi, thank you for the presentation. I also have a question about the what do you call it? You call it extendable sequence. With extendable sequence, you could indefinitely extend the tree, I suppose. And how is that related to your YAML? So because the YAML file also defines the structure of the tree, right?
Yeah. The YAML is actually one level below the extendable sequence. So the extendable sequence was used or is used basically for those nodes and edges where the master control or fleet management system can send you go until there and expect to have 5 more nodes following up. And then with the next update, you get the next intermediate goal and 3 more nodes to follow up. And attached to each of those nodes is then the action mapping YAML.
Ah, I see. Okay. Okay. Does it make it very hard to debug as well? Since everything happens in runtime, then you have to kind of record what has been running in the tree, and because no 2 executions would be the same.
Yeah, that's especially true for the mission execution with the extendable sequence. It is logged quite well because we have every node in the tree has its unique name, and this can be quite well mapped to the mission that we get. So we see the tree that is built up if it matches the mission. But everything else, the tools, you can't just look at it and see where we are at the mission right now. That gets way harder.
Thank you very much.
Enrico?
Hi, thank you for the presentation. So my question is, your behavior tree goes for actions directly, or is there kind of a glue layer? In particular, I'm thinking about ROS action that kind of act as a scheduler.
We have a bit of tooling to easily implement non-ROS actions. So there we are at the action mapping YAML level, basically, where maybe I can jump back. We basically can provide custom nodes to the tree. So some of them are templated and just ROS action nodes that are executed, and others don't use ROS actions. Some use topics, some use services, and some don't use ROS at all. We translate on the behavior tree node level.
Okay, and I was asking this because I think it is possible to have issues with preemption in behavior trees, and the ROS action layer kind of takes care of running actions in the right order and preempting them in the right order. So I was wondering if there was any situation in which not using ROS action produced an issue with preemption.
I can't remember one specific incident. I would have to look in what we have, because I remember nodes that explicitly manage preemption or fix preemption, where it caused problems. So might be but it might have been the action node. So I have to check.
Thank you very much.
Then Enrico, sorry if I jump in here, but if you have imagine that you have 2 branches that are running in parallel, and the second one has a really, really long sequence of, let's say, database lookups, right? And let's say the third one, you're asked to abort because the first branch of the parallel failed, let's say. In that particular case, you have to decide what you want to do with this sequence. Is it, so let's say this handling, do you consider this entire bunch as failed? Are you throwing away the information that you retrieved? What do you do? So these are kind of things that you have to define. So I imagine that your ROS action, yes, it's helping you for the actions per se, but you also have the, let's say, lookup tasks that where you're checking stuff, and still you have to define what you want to do upon preemption.
Sorry. Okay. So I think in at least in the literature and the behavior tree.cpp documentation, it is kind of assumed that conditions, so lookups, are kind of instantaneous, and they never need to be preempted because they happen, you know, in no time. But of course, I see that this is a kind of a abstract. It is not a real. It is not realistic. It is just an unrealistic assumption, and it might not always be the case. So I guess this is an issue too. That even for on conditions, you need to preempt, or you cannot assume they're just instantaneous. Thank you. Yes, that's very interesting.
I think, sorry if I'm following up with this thought. I think here the main difference is not the instantaneous thing, but the how many ticks does a task require. So if it's a single tick, so just after a tick, it returns immediately, either if it's successful or failure, then you don't have to, say, think about an abort, because as soon as you're ticked, there is no, let's say, time in between where there is this abortion that can come in. But as soon as your task will take multiple times, which I guess it's a derivative task that could be modeled as something different as a ROS action, then yes, you have to start thinking about it. I think this is the main difference, because time is, let's say, given in behavior tree by the stick concept, right?
Right. Thanks. Yeah.
Maybe Jannik, I understand you have this expanding sequence, especially like I think it makes sense in combination with the VDA 5050 protocol where it can extend it. But how do you handle this? Will you like at runtime open a new tree or create a new tree, or will you halt the current execution and try to start a new one? How do you exchange the behavior tree definition at runtime?
So the tree, the extendable sequence just returns running if there are no further subtrees, but it knows that there should be subtrees. And then we dynamically create a subtree and load it in this extendable sequence, appending to the children. And
so it returns running if there are currently no children. So then it will.
Yeah, if we are waiting, so we're running the mission. That's where the extendable sequence then says, yeah, everything is fine. We're doing exactly as we are commanded to, even though we don't do anything anymore.
Okay, so that's kind of the sequencing task in a crazy control node, basically. Okay.
Crazy, quirky control node, crazy control node.
And following up with this, error handling, if you can, so how is it done? Is it the behavior tree that is reporting the state? So how do you, because let's say that, okay, let's say that you have these actions that are telling you which tree to run, but then I guess information needs to flow back. And so is it the behavior tree that is giving errors to the server, or how are you reporting back there?
Not the verbose errors. So the general, this mission fails on this step, that's something the behavior tree reports, but what exactly failed is something that is directly reported from the navigation in most cases.
In your presentation, you said that you have you've decorators that own their children versus in the behavior tree where the root node owns everything.
Yeah.
What kind of ownership are you referring to?
I think we're owning, so the pointer owning unique pointers or pointers that gets passed around, who owns the object. And if you're with the standard behavior tree CPP implementation, then when you load your behavior tree, all the nodes and decorators are managed by the loader. But since we can't use the loader, we have to do it, and we do it on runtime. And we decided that basically every node owns its children, especially for this extendable sequence.
Yeah, of course. Yeah.
We need, we remove the extendable sequence after the mission is done, and then clean up all the children automatically.
Yeah, okay, very, very impressive. Yeah.
I don't advise it as best practice.
Maybe not. But I mean, it's a challenge. I mean, I guess there are multiple ways to solve it, right? So, yeah. We also had a similar use case in one research project where they wanted to have a behavior tree that kind of manages a sequence of tasks. And I think they in the end did it with some kind of retry decorator. But yeah, I think it was known kind of a priori what the tasks were, but it's still hard, even if you know it in advance. It's still hard. There's still 10 different ways to do it in the behavior tree, and how to say which is the best one.
While preparing the presentation, I thought about, we're basically, so we have our regular expression that matches with our missions somehow, and we're not building the regular expression in the tree, but we're explicitly copying what we get. So I'm not sure what would be nicer or less effort, less side effects.
One more question. Do you actually have any problems when you get a lot of updates? I assume then for each update in the VDA context, you have to rebuild your tree. So do you get stuck sometimes, or how long does it take to rebuild it?
Super interesting question. We never ran into issues with this. We don't really have to rebuild the whole tree. So that's the nice thing with the standard, that it separates between a tree that is fixed, so base, and a horizon tree that can change. And we don't even care about the horizon tree, and just get the diff, which is, it's quite well laid out with the ID system or the index system they added. So we can just pick up and add whatever the update brought to us and add it to our extendable sequence.
Good. I guess if there are no further interesting questions, I'm sure, Jannik, you will try to continue participating, and if there's something in the future, we can also discuss it later. I'm happy to also discuss this again. I guess we can also talk about this again in a future Deliberation working group.
Sure, yeah.
But now I would actually like to give the word to Enrico. In the last meeting, where I was not really very participating, you had a nice discussion on these formalisms. So maybe as a quick recap, Enrico and I are working in a EU-funded project that is about this deliberation layer, and especially Enrico's branch of the work is a lot about formal verification of this. And Enrico stumbled upon a couple of aspects that are basically not clearly defined, where there's basically a discrepancy between how the book, like this book by Michele, defines the nodes and to the implementation, and also probably different implementations do it differently, and so on. And this is of course very hard for verifying this, but it's still a problem also for people that just want to use it, because it means that it's not really predictable what the nodes do. And yeah, I think in the end of your last discussion, there was also this discussion about this preemption problem.
Yes, exactly. That's why I was curious to see what different approaches could be. Yep. So actually, if you let me share the same slides as last time.
You should.
But
yes.
I just need to find the right one. Okay. And yes, we had this discussion last time. I hope, can you see the slides now?
Yes.
Great. Okay. So yes, last time we saw that I skipped to the meat of last time presentation. There is a discrepancy in terminology between the literature and the implementations, and this sparked a conversation on what a formal definition of behavior trees could be, and how could we set some standard that we all agree on, which would make it easier to kind of work with implementations, work with the theory, and so on. And the more I think about this, the more new questions come up. So, for example, I will take the reactive sequence, which is probably the trickiest of them all. So we have the reactive sequence as it is implemented in behavior3.cpp, and specifically in version 3.8, because the implementation changes from version to version in possibly subtle ways. So already here there are issues on what such a definition should be if we wanted to give a formal one. As Christian was saying, there is an issue with preemption. So what happens is that children are run from left to right, and if one of these children returns running, then the children on its right have to be halted, because they could be running as well, because of the reactive nature of the node. So if, for example, child 2 is running, and then we get a new tick, we run child 1, and the return and what child 1 returns is running, then we have to halt child 2. But this means that, at least in these terms, there is there is some time in which child 1 and child 2 are running at the same time, and nothing says that these child 1 and child 2 are not doing something that is in conflict with each other. Maybe they are accessing the same resource. So what to do with these? I spoke with some people in the field. The answer I generally got is that somehow the behavior tree does not deal with these. Somehow there has to be something that takes care of these issues, and specifically in like the recommended way to use behavior tree.cpp is to use it in connection with ROS action. So when we call actions from the behavior tree, we are not really calling functions directly on the robots. We are scheduling actions on ROS action, but it is ROS action that then decides what can possibly be run without getting in conflict with currently running actions. So this already poses a problem. One way to deal with these could be to simply state that by definition, by standard, the behavior trees don't deal with this preemption issue, and so like a conformant implementation of behavior trees will also have a given scheduler that takes care of running actions in the right order. This is this is a possibility, I guess. It reflects the status quo, but it is also problematic because then there is a huge amount of undefinedness. So we know that the behavior tree takes some actions, but we don't even know if they are run in that order because the scheduler might do things differently. And this is already a very hard issue. I don't know the answer for. Maybe someone knows the answer, and it would be great to know. Like, please raise your hand in the discussion if you have any thought on this. Another issue is that, as you see in the code, when it is time to preempt the children, so to halt them, the code just halts them all from I+1 to n. So it starts from the first child, halts them all, and not all of them might be actually be running. So we are calling the halting function also. We are sending the halting signal also on children that might not be running. Nowhere it says that halting doesn't have side effects. So this also raises the question of, do we want to halt also children that are idle, or should we kind of filter the children to halt only the ones that are currently running? This again is a behavior that I don't think it is clearly defined, and both ways sound sensible to me, but I don't know if there is a consensus in the community of what the most sensible behavior should be. So,
Enrico, before you jump forward,
yes.
So basically, what you're saying here is that in literature there are three main, let's say, question marks. There is first one is defining this halt function for the children. Second thing is what to do with the halt. So is it possible to apply this halt method on the children? And third thing is what to do when the halting actually takes time, because that's like the most tricky thing, and that's where you go to the scheduling part, which I think it's a horrible idea, because you could have a behavior tree that is idling, and therefore you're losing the entire reactiveness of the behavior tree. So I think like this last one is the main, let's say, while the other two are, let's say, missing definitions. I mean, calling halt on idle nodes, I mean, you can just define it as a no op and problem solved, right? So it's not a problem. Define this halt function for things that are really quick. I think it's also not a problem programmatically wise. So you say, okay, you have to fail really quick, and it wouldn't be, I think, too hard to define. I think the core issue here is that when you have a halt function that is taking quite some time. So I imagine here an action, a ROS action being aborted, that it takes seconds. You don't really want to have the entire behavior tree stalling, because you could have another node that is changing value, and therefore you don't want to stall. So I guess here your core question that you're trying to understand is how to handle long running halt methods, because the others are, to me at least, kind of manageable. Or am I understanding this wrong?
So sure. I mean, I totally agree that the long halting method is an issue, is a particular issue. Yes, I agree that it is not really an issue to define what to do on when halting a node that is idle, because you can define it as a no. That's clear. I'm not sure why it is not an issue if the halting is instantaneous, because even if it is instantaneous, it only gets called after ticking the previous children, and ticking can take a long time. So even if the halting is instantaneous, before you can you arrive at calling the halting method, you have to wait for the previous ticks to end. And so in this gap of time, something might happen. I don't know if...
But that is a problem that you still, I mean, this is a problem that you always have. I mean, if you have a child 1 that is hanging, that is just holding, so the stick is taking, I don't know, 3 seconds, then it's a problem with child 1. So I don't understand why it's a particular issue for child 2. I mean, at a certain point in time, for what concerns child 2, you will know if child 1 succeeded or not. And then from that point of view, from that point in time, if child 2 returns, let's say, after really a split second, where is your issue with the halting? I mean, you just return that it stopped, and then you handle it. I don't understand where this issue. So why you say that there's a big issue here? Maybe it's just me that I'm not seeing it.
So my issue is that ideally, if, let's say, we are ticking child 1, and at the end of the tick we realize that child 1 is running, so we need to halt child 2. What we really would have wanted to do is to halt child 2 first, and then tick child 1. So we would need to kind of see into the future and know that in the case of this reactive sequence, child 1 is something that will need to run and also take time. So we should first preempt the other children to let child 1 run, say, without obstruction.
But why do you have this assumption? Why is this a requirement? To foresee the future?
Because if child 1 returns, immediately returns success, then because maybe it is a condition that is true, so I tick it and immediately returns a success, then I don't have a need to halt child 2. Maybe child 1 is just checking a variable, immediately returns success. There was no reason to halt child 2 to just read a variable. But if child 1 ends up calling some complex task and it takes time and then returns running, then I have a child 1 that is doing something, taking up resources, and child 2 is doing the same in the meantime, and they might get in conflict.
Your problem is that if child 1 is also returning running, and therefore you have to, so child 1 and child 2 are durative actions that are both returning running, and with this sequence, child 1, let's assume it's done, then child 2 starts, then I call back child 1, it would be returning running, and that's the problem. Okay, understood.
Yes, that's my problem. I don't know how much it is considered a problem in practice and in the community. Maybe these things happen all the time and it's not so problematic. But what I observe is that most of the times when in a behavior tree there are reactive sequences, children tends to have kind of a condition, tend to be formed as a fallback with a condition that act as a guard, so that you only know that you need to run the child if a certain condition is false. And so this allows to skip quickly to the child that really needs to run. So, I mean, it seems to me that in principle, there is an issue that developers kind of deal with by constructing behavior trees in a sensible way, which is good, but also I mean, it is a problem that the definition of behavior tree in itself is not, it's problematic with respect to preemption and forces developers to kind of handle them by, manually.
I think also the problem is that this whole halt method is not really formally, I mean, it doesn't really happen in the literature. It's more like an implementation detail. It's handled like an implementation detail. But like my assumption would be that we could solve this by saying that both the tick and the halt functions must take X amount of time at maximum. So kind of we can simply say in the standardization, that's also something that you could maybe in an implementation kind of govern, that these tick and halt functions both only take a given amount of time and have some kind of watchdog that goes off as if it takes longer, because this would indicate to the developer that there's maybe a problem, because then you could kind of, and because this assumption, like the problem that you mentioned, I think this would, the behavior tree as formalism would solve this by this discretized time. Like it would assume that the next thing in a sequence only happens at the next tick. And so as long as you can guarantee that everything that's supposed to happen in this tick actually doesn't take too long, so actually happens within this delta time that you tick your tree in, I would assume, or I would hope, this would solve this, because then kind of the situation may have changed, but not during the one tick. You must not handle these changes, right? You can handle them in the next time you're ticked. Yeah. That's what it would be at least my idea.
True, but you maybe in ROS it's a bit hard to. It's a really strong constraint, right? Because if you're saying that the ROS action should abort or preempt in X seconds, then what do? Do you forget the goal state? So there's a bit of a question mark. True. I mean, I agree with you, Christian. But I think also what Enrico said with having multiple children that are durative and can return running is definitely a problem that currently people are just using this mem sequence, right? So you just remember which child you have ticked, and then you jump to that, because usually sequences, so the active sequences, how they are defined, usually you have at least the n-1, let's say, children usually are non-durative, and then maybe you have the last one that is durative, because you don't want to have exactly this two running at the same time. So completely agree with Enrico. This is a bit of a question mark that so didn't realize.
I can also add that there are other possible solutions to this issue. All of them have downsides. I mean, all of the ones I can think about. One is to redefine the reactive sequence in a way that, in some sense, it prevents this from happening by halting the kind of the rightmost children first and then running the leftmost. And the exact details of how to do this, I mean, are up for discussion. I'm sure there are many ways to handle this, but the real issue is this is non-standard, and the implementations don't have this kind of node. And I mean, we need to. The point is, we are not proposing. The point is, are we proposing a new implementation which we think is better than the current ones, or are we trying to give a standard that reflects the status quo? So I don't think that proposing a new definition would automatically be accepted by the community and result in anything good. So if we take the reactive sequence as it is more or less commonly defined, because also some slight details can vary, but the core idea is that if we take that as the definition, we have, like, we cannot make such huge changes in the node logic. So I guess this is a really an open question. There are, I mean, I see potential solutions, but all of them have downsides. I don't know which ones are more or less acceptable by the community.
Yeah, I mean, one path would be also that we try to give rules to how the actions should be implemented. Because if you, for example, say an action must, like the tick, must not take certain time and stuff like that, and things must be preemptible. And so, for example, like a very hard rule would be that kind of no two actions access the same resource, right? So if you would say every action must be kind of completely independent of every other action, that would basically solve this problem. But maybe it would not be suitable, but like this would be also a way where we kind of don't really have to change the implementation. Hopefully not in a major way, but we can maybe give guidelines that would also help people how best to implement their actions, or kind of also, I mean, that's also something that's like really not clear, like how many people do actions with ROS actions, right? They do behavior tree actions with ROS actions. Also nice that these are the same names and mean different things, right? But how do you map the states, the return states of the ROS action to the return states of the behavior tree actions, right? And it's also completely undefined, that everyone does it how they think it should be done. But if you kind of can get to a agreeable solution, then you also have, like, in the end, you end up with like kind of more reusable code and stuff like that.
I mean, I agree with you, but I mean, I think the issue here is that robotics mandates some. It is impossible to mandate certain conditions. For example, if we have a humanoid robot that has an action, raise your hand, then the preemption means not just stopping the hand, but also possibly lowering it. And lowering the hand requires a certain time that cannot be really changed. So mandating that preemption takes a very short amount of time will not be possible, because the time to lower a kind of a piece of art, to lower hand is what it is. So I think this is something that makes robotics extremely difficult.
I'm not quite sure, but I think there's also an example in the book where they have something like this, similar to your hand example, where something needs to be reverted. And I think how they solve it is that they have an explicit action in the tree as well that would then lower the hand. And so the preemption would be just stop your current motion. And if you kind of also kind of consider this case in your tree design, at another point, you would then have this action that lowers the hand again.
Okay, but
maybe it's not a general case, but yeah, generally this reversibility is of course a problem in robotics. Yeah.
Sorry, this example requires the developer of the behavior tree to handle it, though.
Yeah, exactly. Yeah.
Mm-hmm. Okay. So, I mean, for me, a really big problem is is there a definition for behavior trees that is safe by definition, does not require developers to be smart, or said in another way, if you write a behavior tree badly can the robot break? Can you break an expensive robot just by writing your behavior tree wrong?
Yeah,
I
I
think this
guess
is something that possibly should not. I mean, of course, will always be some possibility, but as much as possible, it shouldn't be happening. So at least ruling out kind of bugs that can arise from badly executed preemption would be a big thing. Like you have an assurance that your robot will not break because you didn't do preemption properly.
I think this would be a strong constraint on the behavior tree to say we want to make behavior trees that always produce safe. Always produce safe behavior, right?
I mean, sorry, to be clear, I'm not saying that the behavior tree should prevent instructing a robot from falling from a cliff. Of course, if the behavior tree says fall from the cliff, nothing will prevent it from, nothing will prevent the robot from breaking. What I'm saying is preventing situation in which the robot breaks because a certain action was supposed to have been stopped already, to have been preempted, but it hasn't been, and so like you are kind of using two resources at the same resources in two different ways, and this leads to a failure. These I feel it should be, preventable.
Yeah, but I mean, it is also something that you could solve on this action level.
Yeah.
If you say,
Sure.
I raise my hand, and then on the other side, I call another action that does something else with the hand, then you could also say it is the task of the other action to make sure that the hand is where it's assumed to be. I mean, I guess it would be a question where you implement this, but yeah. Yeah, we are already 10 minutes over time, so thanks everyone again for the nice discussion. Definitely we can iterate on this a bit in the next meeting. Like the long-term goal that we discussed already would be to have this in a maybe ROS enhancement proposal, but also like a short research paper or something would be maybe a place to put all the pseudocode and say we provide this as a reference implementation or something like that, like a reference pseudocode implementation. We can work on this, I guess. Guillermo?
Yeah, the ROS enhancement. So how do you imagine it? Because I mean, BTCPP is something that is also being commercialized. And if we are pushing improvements there, then I guess, I don't know, I had a discussion with Davide that, for example, Magazzino and Davide, we're a bit in a competing terms. There we have to be a bit careful, let's say. When it's about open, like going in publication, I think it's not a problem, but if we're targeting BTCPP, then there is a bit of stuff. Also, there are patenting issues because we have patents out and so on. So there, it's a bit, let's say, I'm also like struggling here because we have our stuff that I don't know what we can say, what we cannot say because patents are out and so on. So there is a bit of a question mark. We would be definitely interested in knowing how we want to follow up, because if it's a research, it's not a problem. If it's a BTCPP enhancement, then there might be some issues. I don't know if we are the only ones.
I would prefer to have Davide on board with this as well. So I hope maybe can also talk to him sometime. I don't know how easy we can impose changes on behavior-treated-CPP. We have to see how this goes. But if we have kind of like the better we can support these suggestions, the better it is, I guess. And if this ends up with a completely new that a completely new implementation is required, then it would be maybe not a super productive outcome, but it would still maybe highlight what the issues are.
So if I can say something about this, from my point of view, like as someone that started to read and research about behavior trees, a very big issue is that the situation also of the literature and documentation is very, very confusing. So of course, I don't expect to impose changes to implementations, but I think it would be already a big step forward if there was a kind of abstract definition that the community agrees upon as something that says the standard version, and which can be referred also by implementation to say, well, we are compliant in this, but we do this other thing differently for whatever reason. And I mean, at least it would be easier for people to know what is happening, because right now, I mean, I must say some things are you can only find out about some things only reading the source code. Not even the documentation is enough to really kind of understand the fine details. So even just from an informative point of view, to allow people to understand what happens would be a big step forward. Then, of course, if the implementations think that the standard actually makes sense and they want to move towards a standardization, that is very much welcome. But of course, they don't expect to mandate it or to require it. That's not possible, clearly.
Good. Then, thank you very much for everyone, and I will try to get the recording online before I go to holiday, and then we can watch it all again. Jannik, will you be able to also send me your slides? Is he still here? I don't see him. Yeah, then I will send him.
We will share the slides. I'll take care of it.
Yeah, thanks, Philip. Okay, have a good week, everyone.
Thank you. Bye-bye.
Ciao.
Thank you. Bye.
Thank you. Ciao.
Ciao.
Bye.